Okay, so welcome to this, the second part of my presentation about statistical analysis in DEA models. In this part, we're going to talk about two very important techniques, somewhat related techniques also. One being subsampling, and that's important because we know that the efficiency scores depend a lot on the size of your sample and the number of inputs, number of outputs, and therefore it might be relevant if you want to compare different benchmarking studies to correct at least for the size of the sample. So that's one technique that we're going to talk about, and then we're going to spend most of the time on bootstrapping, which is a more general technique that can be used not only to create bias-corrected efficiency scores and confidence intervals of bias-corrected efficiency scores, but also can be used in the testing of hypotheses of various sorts. I'll show how to test, for example, for economies of scale in one of these models. So we have to dig in. It's a relatively long presentation, approximately 1 hour, I guess, but we'll see how it goes. Okay, so first the bias and sample size. Remember that the way that we estimate the technology is as the smallest subset of input-output space that contains all the data we have, and that fulfills a certain minimum of regularity assumptions. And that means that assuming that those regularity assumptions hold in the real world, then what we're creating is an inner approximation of the technology. And in turn, this means that we are going to get we're going to get upwards biased estimates of the input efficiencies. So basically, firms are going to look better against the DEA technology than they would have looked compared to the real technology. So this is the bias problem, and what we're going to talk about is how to correct for that. To illustrate it here, you could imagine that you have the true frontier, which is this smooth line here, and then you do some observations, and they have the various companies are represented by the black dots, and they have introduced a bit of inefficiency. So they have, instead of spending this amount of input to produce this output level here, so they've used this amount of input. And this guy over here, for example, he has added some slack to the production process, or he hasn't been quite efficient in his organization. So therefore, he has an input or a cost maybe all the way out here, okay? And since everyone has some problem in the organization, or problems with slack, or have maybe insufficient incentives to really operate efficiently, then all the observations are going to be somewhere to the right of the true frontier. And so when we estimate the DA frontier, we get this one here. And then if I evaluate the performance of this guy, for example, I would say that, okay, he could have reduced his inputs. He could have saved costs down to this level here. He would have moved here. But in reality, so that gives me one efficiency score, let's say 0.8. But in reality, of course, he could have moved even further. He would have moved down here. So this whole move might have given an efficiency score of 0.7. So there's actually like a 10%, 10 percentage point difference here, and that's what we call the bias. So that's really the difference between the DA score and the true efficiency score. So that's a bias problem. Oh, that is a bias, okay? It's good to know. The problem, however, is that the size of this bias is not the same in different parts of production space. So you can see down here, you have a huge difference between the observed, between the DA estimate technology and the true technology. Up here, you have much less of a difference. So the bias in this area here is much less than it is here, and it is up here. So you can say, sort of intuitively, it also makes sense if you makes a lot of observation in some parts of production space, then you probably get a better approximation of the technology in that area, the underlying true technology. You get a better estimate of that than you do in more sparsely populated parts of production space. Okay. And of course, you could also say that if you have few observations, you are most likely going to get, if you have few observations, maybe you didn't have this one, then you would have an even more conservative estimate of the production possibilities. So this bias problem impacts the efficiencies. We know that efficiency E, input efficiency, it decreases when you have many observations, also when you have few inputs and outputs. And it also decreases, so you look less efficient if there's a lot of similar companies that looks more or less like you, because then this bias in this densely populated part of the production space is smaller. And that means that you have to be really careful when you compare results from models that contains different number of DMUs, different inputs and outputs, and different degrees of similarity between the firms. One of the first time that this was discussed in the literature was actually a comparison of the efficiency of distribution companies, and I think it was in New Zealand, one of them, the other one was at least Sweden. And what the problem there was that you found a certain level of efficiency in New Zealand, and you found quite a different level of efficiency in Sweden. But then people realized that might just be because when you estimate based on New Zealand data, you have way fewer comparators than you have when you use Swedish data. There are so many more distribution companies, or there were so many more distribution companies in the Swedish data set than in the New Zealand data set. So the fact that the Swedish company looked less efficient might just be because of the bias problem being smaller in the Swedish model than in the New Zealand model based on New Zealand data from New Zealand. Okay. I've seen it also in other areas, like for example, you do an analysis of two sectors. For example, waste handling could be done by landfill, or it can be waste can be handled also by incineration. And then if you have maybe way more landfill sites than incineration sites, then you're most likely going to look more efficient in incineration compared to landfill. Otherwise, I mean, and that might even, in the one I saw, there was even another problem, that was that the number of inputs and outputs that was used was not the same, and therefore one couldn't really compare them. So, but it might be very tempting for people to look at it and say, okay, we have a certain level of efficiency using this technique to handle waste. We have another level of efficiency using this technique to handle waste. So maybe here where we have a relatively low efficiency, maybe we should try to regulate them, or maybe we should try to introduce some kind of competition between these handling facilities. And there's no reason to do anything over here because the efficiency is actually already very high. Maybe the efficiency looked high because there was very few firms to compare, while over here there was a lot of firms to compare, and therefore the efficiencies look lower. So one has to be really careful with that. And there's actually a very simple trick to use. So this goes back to this old comparison of New Zealand and Swedish companies. The basic idea is that you take the size of the smallest population. So you have two populations you want to compare. Maybe you have 30 in one and 200 in the other. Then what you do is that you pick out 30 from the big sample of 200. You take, for example, assume you had 30 in New Zealand and you have 200 in Sweden. Then you take a subsample of 30 Swedish companies and you do an efficiency analysis of those, and then you find out what is the average efficiency. Then you draw another subsample of 30 from Sweden, and then you see again what's the efficiency there, because now you're comparing the efficiency level in New Zealand, which was based on 30. You're comparing that with what 30 companies would look like in Sweden. Okay, so you're going to get several different observations depending on which subsample you get. But so that basically just means that you get a distribution of the efficiency score, and then you can compare that to the number you had in New Zealand. So it's basically the smallest population that determines what kind of subsampling you can use, and you just replicate the small samples in the big by subsampling in the big sample. Okay. So compare models based on different population sizes. You subsample small sample size from the large population, and then you compare the small sample size efficiencies, because now they're comparable. This, as I said, was done in Sweden and New Zealand when they had to be compared. We are using it in a lot of other projects also. For example, we are doing a project right now where we are looking at the impact of innovation. And in some industries and some innovation types, we have relatively few observations, maybe 100. And in other industries and innovation types, we might have 1,000. So if we were just to look at efficiencies in those two subsamples, it would be misleading. Those based on a small population would tend to look much more efficient. And so what we do is we subsample from the big industry innovation group a number of times, so that we get results corresponding to the smaller sample size. Okay. Another way to actually look at some of this, and this goes back to sort of some of the more practical tools you can do, is that you can get some impression of these problems here. Is also to look at this inefficiency step ladder, which we call it, as we call it in interactive benchmarking, or just the efficiency step ladder. The idea here is that you take for every firm, you see what happens if I remove one firm, if I remove two of its peers, and then another peer might pop up, but you get an idea about how certain are you in the evaluation of me, for example. If I have a firm and if I look bad, and then you remove one of my peers, I continue to look bad, you remove another one, I continue to look bad. So maybe you can remove maybe certain 20, 30 comparators, and I still look bad, okay? Then we're pretty sure that I'm actually bad. But if you were just to remove one or two, and then I all of a sudden look good, you'll feel less certain about the evaluation of me. That's not directly related to the bias, because actually the fact that you can only remove two and then all of a sudden I'm on the frontier, it might actually indicate that I'm in a very sparsely populated area, and therefore there's more bias in the evaluation of me. So on the one hand, if you have many observations, you can be quite certain about the evaluation of the company. But if you have few, you are more uncertain, and you also have more bias, you can say. So there's some things you can think about and play around with. So how can we handle this? We can handle the size to some extent. In this way, if you're just interested in average efficiency, but you might be interested in correcting the individual firms for the bias we have in the evaluation of that firm. And to do that, we're going to use bootstrapping, which is the subject of the next and the main part of this presentation. But before we do this, let's try to take a few questions. Okay, so what is bootstrapping? Bootstrapping is actually a well-known statistical procedure, and it can be used also in the evaluation of DEA models. One has to be careful, though. One cannot use one might be tempted to do like naive bootstrapping, but one has to really figure out which part of the data set you want to resample, so to speak, or which you want part of the data you want to bootstrap. Okay, so basically, bootstrap is a computer-based approach to calculate accuracy of statistical estimates. It's important. I'll have another slide on that, but it's important that you don't really generate new data. You just get an idea about how precise the estimate that you calculate on given data, how precise that estimate is. It's a little bit, it sounds a little bit weird because at first you might think it's a little bit weird because it's like you have your data and then you just subsample from the data and then you get a result, and then you try to subsample from that data and you get a result. So it's like you're reusing your own data. You only have one sample, you're just reusing that a lot of times. So it seems like you get sort of superpowers without really getting any new data. And that's also why some people, it resembles this Baron von Münchhausen, which I don't know if you remember the story, but he was a baron and he was out riding and he got stuck in some mud, and then the way he pulled himself out of the mud and his horse out of the mud was basically that he tightened his legs around the horse, and then he pulled in his bootstraps, and then the story is that he was able to pull himself out of the mud. And it might seem sometimes that at first bootstrapping might look like some magic trick, like you're trying to pull yourself out of the mud without really having anything to hold on to. But there's actually a theory behind it, and I'm going to show you how it actually works. So hopefully you can appreciate that. The idea is to sample with replacement from one's own data to create a so-called replica. Okay. And then in that replica, you estimate whichever estimator you're interested in. For example, mean efficiency or median efficiency or something else, scale efficiency, whatever you want to evaluate. And then you pick out a new subsample of the data, and you do so repeatedly. And in this way, you will get different values of that estimator, like scale efficiencies will be a little bit different depending on which unit you picked. You picked with replacement, by the way. So you will get a little bit different values each time. And then in this way, you kind of get an idea about the distribution of my statistics on this data set. So you can look at it like this. It is a way to estimate if you assume that the original sample is a good approximation of the underlying population. Okay, so you kind of see that you believe that your sample is representing, in some sense, the underlying population, and then you try to estimate just the kind of uncertainties there which are involved because it's only a subsample of the population. So here's an example. Let's see, what is the mean of, you have some numbers and you're wondering what the mean is. And the numbers here is 1 to 9, so it's relatively easy. The mean is 5. But you're now wondering, okay, but how certain, I've made this observation and I've seen that the mean is 5 in my data, but how certain can I be that the mean is really 5? So what you do instead is now you take a subsample of 9 numbers from this from this set here with replacement. So maybe next time I pick 1, 2, 3, 5, 6, 4, 5, 8. So you see that we repeat 5 twice and we repeat 3 times. And now in this case, the mean in this subsample becomes 4.11. You can pick another subsample with replacement. Now I get 5.55, and the third one you get 3, and then you get 5.11, and so on. And that means that you can get an idea about what is the what is the mean when you take into account that it is a little bit there's a chance event involved in choosing observation from the population. So you can look at the distribution of these means over here, and then you can evaluate whether a mean of 5 is really a high number or a low number. Maybe there's a lot of this approximation of the population could easily generate smaller values of the mean, or maybe it can also easily generate higher values. So you get an idea at the mean. How can you evaluate whether a mean is this mean of 5, is that a low one or a high one? Okay, so it's slightly more general. So you have always an original population, well, you have an original population, but then you have subsample, you have a sample from that. And we believe that that sort of represents the true population. And then what you do is that you create subsamples from this initial sample, or which we call the original population. So you pick out n of these guys with a replacement. Okay, that gives me bootstrap sample number 1. Then you do it again, then you do it again. Maybe you do 2,000 times, which is a common number to do it. And then in each of these cases, you can calculate all kinds of statistics. So you can calculate the mean, or you can calculate the maximum, and you can calculate the minimum, or whatever. And by calculating these numbers, then you get like 2,000 examples of what the maximum is. You get 2,000 examples of what the mean is, and so on. So you get the possibility to estimate the distribution of these statistics, even if you cannot calculate them directly. So that's basically the idea. So you get these B bootstraps, subsamples here, or samples, and then you get you can estimate the parameters you're interested in those bootstrap samples, and that gives you the distributions of the various statistics that you're considering. It's important to emphasize, before getting any further, that the bootstrap method is not a way to reduce error. It doesn't generate any new data. What it does is it tries to estimate the error. Okay, it doesn't reduce the error, it just estimate what kind of errors might we make given the size of our observation of our data set. The bootstrap distribution usually estimates the shape, spread, and bias of the actual distribution. So you can use it to estimate properties of the underlying population, okay, in terms of shape and spread and bias and so on. But remember, Bootstrap does not replace or add any new data. It's not that we're just reusing the same data and again and again. And then one has to be careful also. It's not all cases where you can really bootstrap. You can't bootstrap it if the data set is very small. And you can't bootstrap if you believe there's too many outliers in the data set. And with time series data, the bootstrap is based on the assumption of data independence. So there are some conditions. Most importantly, maybe, you should really believe that the observations you have are independent draws from the underlying population, okay? So it's not that you can always use Bootstrap, but there are many cases where you can use Bootstrap. So I have a small example here just to get you started, and you can try to do it in the R code also. So let's assume that you are interested to know not only the median value of a population, but you want to know the standard deviation of a median value of an observation of a population. Okay, that's a difficult thing to calculate. Actually, there's no simple formula for the standard deviation of the median observation. If it had been the mean observation, then we know that we could take the standard deviation of the variable itself, and then we could have divided that by square root of n. But in this case of the median, there's no easy way to find the standard deviation. So how could you do that anyway? Well, you have some observations, then you select B independent bootstrap samples, which we'll call x1, x2, and so on, up to xb, superscript b. And each of them is drawn from the data set with replacement. And then here I have, like, maybe assume that I have a population initial data set of 100. Then I have this one is a vector of 100 observations. Some of them will be similar, some of them will be different. And in that I can calculate the mean. So that will give me the mean for the bootstrap subsample number 1. And then I can get the mean for the bootstrap sample 2, and so on. So I get if I did a 2, I get B observations of this statistics, which is really these are the means, right? And then you can, so you basically have a B observation of means, medians, and then you can just take the standard deviation of these observations here, like down here, where I take the observation minus the average observation, and then I square them, I sum them, and I divide by 1 minus the number of observation, and then I take the square root, because I don't want the variance, I want the standard deviation. Okay, if you want to try that, it's really, really easy. You go in, you call the Bootstrap library in R, you put in your observations, and then you define the function, which is that once you take out a subsample, you will calculate the median value of that subsample. Then you make 200 repeated bootstrap, or you 200 times you pick a bootstrap sample, and you calculate the value of this function that you have, and then you take the variance of that value that you have picked, and you take the square root of that, and you take, you can also calculate the mean, of course, and you can even draw a histogram on these. So this is just an example you can draw a histogram of the 200 values here. So this is just an idea to give you a first idea of how you can use bootstrapping. Because when we start to do bootstrapping in DEA, it looks a little bit more complicated. So it might be useful just to take a look at this and see how it works in the simplest possible case. So let's go to bootstrapping in a DEA context. And there's kind of a naive way of doing it, and there's a better way of doing it. The naive way is the following. We just look at the efficiency scores of the observations, and then we try to bootstrap them. Or maybe I should have had it like a... Okay, let me just, I think I dropped one. Yeah, I dropped one here. So let's assume that, why is it relevant to do this bootstrapping? Why would we like to try to do bootstrapping in DEA? Well, if you get an efficiency score of a firm which says it's 0.9, the input efficiency is 90%. You would really like to know, is that a significant difference from one, or is just different from one that you get because of luck? Is this firm really efficient? So ideally, what you would like to do is actually to create like a confidence interval around that. That would be really nice if we could do that. We're actually not going to be able to do that directly, but there's a bias-corrected version of this, which we can find confidence intervals on, but I'll explain that in detail as we go on. But that's one motivation for it. And then the other thing is that we would like to somehow correct for biases. As we talked about, EI is always higher than the true EI, namely if we compare to the underlying technology. So we would like to estimate that bias and then correct for this bias. And we are particularly interested in that because we would like to correct for the fact that for some of the firms there might be a large bias because then in a not very densely populated part of the production space, and in others the bias is much smaller than that. And so what we're actually going to be able to do is we're going to do bias-corrected efficiency score, and around that bias-corrected efficiency scores, we are able to determine a confidence interval. Okay, so that's what we can actually do. Because really what we can get out of bootstrapping is an idea about how much that bias will vary depending on the location of the points. So it's not quite what you would immediately like to get, but it's for the bias corrected efficiency that you can get confidence intervals. Okay, so there are two ways to do this. The naive way is that we look at the efficiency scores as observations, and then we just bootstrap among those, similar to the case I looked at before. Just bootstrap these, and in that sense you'll get some kind of an idea about the distribution of these bootstrap values. It presumes, however, technically it presumes that all these efficiency scores, they come from the same distribution. But in reality, this is not the case. It probably also depends on the x's and the y's, what the efficiencies are. So in that sense, it is not it is too simple just to do the naive observation. It is a better idea is to look at the original observations and then to bootstrap them. So basically, you have your original input-output combinations, and now you try to take a bootstrap sample out of this with replacement. So you get another sort of set of n observations. Some of them might be the same. And then you do that repeatedly. And in this way, you get an idea about how the technology and the technological frontier is shifting back and forth. And therefore, you get an idea about how precisely do we know the location of the frontier in different parts of production space. And you get an idea about the bias towards the true frontier. And I'll show you that in detail. But the idea is to bootstrap on the underlying input-output combination. So we get bootstrap technologies. And for each replica, we calculate the efficiency of firm number I relative to this new technology. And in this way, we get a distribution of the efficiencies of firm I against the bootstrap technology. And using that, we can calculate the mean and the variance of this distribution. Or we can even do better, we can use the distribution of these observed efficiencies against not the true frontier, but a DEA frontier. And then I'll show you some pictures. Then we can use that to also guess that you will have a similar distance between the original DEA model and the true model. That's basically the idea. One of the most popular bootstrapping procedures for DEA is developed by Leopold Simard and Paul Wilson. If you really want a fast bootstrapping procedures, as you can imagine, can be quite demanding in terms of computer times. And so we have one in the R package called benchmarking, but Paul Wilson has another version of Bootstrap, which is running fast. If you have really big data sets and you think our procedure is running too slowly, you might want to try to consider that. It's not directly available from the R repository. You have to contact Paul Wilson, and then he might give you access to this these procedures. Anyway, the things they do is that it's a little bit like the better approach before, where you bootstrap observations to span the frontier and to span the technology. But they don't just, and as part of that, you have to introduce inefficiencies, and you do that by picking from the original inefficiencies, but they don't pick directly from the discrete distribution of observed inefficiencies. They smooth the distribution. They use like a kernel estimator in the resampling procedure, but I'll illustrate that also. So in a few steps, you can say that their procedure is as following. You use the original data set, and then you calculate DEA efficiency scores. Then you create a kernel density estimator of the efficiency scores. So that's the one you're going to do some draws from. And then you move all the DMUs to the comparative point on the frontier. So now you have the starting frontier. And then you create a pseudo data set by dividing the input values from here with values obtained by drawing randomly from this kernel density estimator. And then you calculate the efficiency scores compared to this soda data set, and you repeat that a lot of times. Okay, to really get an appreciation of this, it's easier to look at some pictures, then you can, I'll try to explain what is really going on, because it's like a lot of steps here, or it's a little bit sort of abstract steps maybe to the first time you see it. So let's take a closer look at these core parts of this procedure here. So the idea is that you do a kernel estimator. Okay, so if you have some observations of efficiency scores, it's going to be maybe look like this distribution here. The kernel estimator is just a way to get a more sort of smooth distribution. So instead of thinking that the true distribution is corresponds to this histogram here, you say that probably it's an underlying continuous distribution, and you might estimate it with some kind of a continuous function like this. And exactly how many details of this continuous function you will have depend on the bandwidth in which you try to spread out the observations. The idea is actually quite simple. So if I have an observation here which is around 0.7, I can add or subtract. I can add like a random normal distributed random variable to that, and then so it means that if it is 0.7, then maybe it becomes 0.71 or 0.72 or something like that, and it can also become 0.68, 0.69. So you basically, around every point, you create like a normal distribution, and so in that way you spread out. You say that, okay, we have observed it in 0.7, but really it comes from this. We spread out the mass of that point with a normal distribution, you can say. And that also means that you get a more sort of smoother and smoother approximation. The kernel estimator becomes smoother and smoother. The larger the variance the larger variance you have on the normal distribution that you add to the actual observation. So basically, any actual observation is you add some noise to it, and the more noise to it you get, the higher the variance of this noise term is, the more smooth an underlying continuous distribution do you get. So when they have to go out and pick efficiency scores, they will not pick by saying directly from these columns. They're going to pick randomly by saying, okay, there's a relatively high probability here. So they'll use this probability to do the picking instead. Okay, now remember there was all these tricks about you had to create an efficiency model, and then you had to project some points on the frontier and stuff like that. So let me try to explain the subsequent steps that they talk about in the procedure. And at the very end of this whole discussion, I'm going to give you the details of the procedure, but now we want to get the idea of what is going on. So here's what is going on. I have my observation A, B, C, D, and E, all the black ones here. And I can estimate a DEA model here. The first thing I do is that I project all points to the frontier. Because remember, D and E, they were actually inefficient ones, but I could, of course, project them to this frontier here. So now I have an initial DEA model where all the points are sitting on the frontier. It doesn't change the frontiers that I project them, but it is going to be useful because in a split second, I'm going to move all the black points back to all the frontier points. I'm going to move them to the right. And that's we do by selecting from this kernel estimator. So we select efficiency levels from the kernel estimator with reflection. Reflection has to do with, I have a very high point. I should maybe have explained that. If I have a very high point, so efficiency of 1, so if I add a normal distributed noise term to it, then sometimes this efficiency will look above 1. And so I basically reflect those numbers back on the other side of 1. I don't just reflect them back to 1, but if it is 1.1, I reflect it back to 0.9 and so on. So in this case, I don't get like a real big discrete probability mass in 0.1. Anyway, so that's why it says with reflection here. So you project all the points to the frontier first. So now we have this frontier here spanned by A and this red and this red and this red B and this one here. Okay, and now for each of these, each of them you introduce some inefficiency, and you do that by picking the efficiency of firm I as a random draw from this kernel estimator, the efficiency of point B as a random draw from this kernel estimator, and similar also for the red ones here. Okay, and this random picking inefficiencies, that will give me these green points here, a green one 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 here. So for example, for A, it's relatively close, so it means that you picked from the right, sort of you picked the value from the kernel estimator, which is a high value. So you picked, maybe you said that maybe the efficiency of this guy that you're going to observe is 0.9 or 0.95 or something like that. While for B, you picked a lower number from the kernel distribution, so you get projected further to the right here. Okay, so this is the idea. You have this as the underlying model, but now you create like a new model here. And then by doing this many times, you can actually get an idea about how much the technology varies. I mean, it might be that, for this guy here, sometimes he's here, sometimes he's here, sometimes he's over here, and so on. So there'll be a lot of variation in the technology up here. There'll be much less variation in the technology down here, because here we use we have several points which are close to each other. Okay, so in this way you can get an idea about how uncertain is the variations in the different places, because it has to do with how variable is the technology in those places. Okay, and now the next trick is that you can figure out that there'll be inefficiencies in this. The one I showed before, there's going to be inefficiencies. So for example, this green point, he's inefficient, and this guy is inefficient. Okay, and it's inefficient relative to the green technology, but it's also inefficient relative to the black technology. And the trick is that this green one here, the difference between the green and the black, that is like a bias that is created. If we know that this is the underlying truth, what kind of biases do we then create by using this green one? And that kind of imitates how the original data was collected, because you had there an underlying technology, but that was unknown. And then you observed this A technology, okay, or the black technology. So we didn't know what the bias was because we didn't know the underlying one. But now we know the underlying one. It's represented by the black one. And now we see how much bias do we introduce when we go from the black one to the green one. Okay, so sort of you get an idea about the bias in different parts of production space. So this is the idea. You say that the bias you have between the normal DEA, the black one, and the underlying true technology, which we didn't know, that bias is approximately the same as the bias you have when you compare an observation to the green technology rather than compare it to the black technology, piecewise black technology. Okay, so this bias here is approximately the same as the difference you have between what I in the previous slide showed as the black piecewise linear technology and the green one. So that's the idea. So you can get an idea of the bias, and once you have that idea of the bias, then you can just subtract that from the original efficiencies, and then you get a bias-corrected efficiency score. So I've tried to illustrate it here in a little bit more details, and I realized that it might end up looking a little bit complicated, but let's try to go through it. I've kind of introduced the different elements before, so now we can take a look at it. So I have an underlying one which I don't know, technology. I have the first initial DEA model, which is the black one here, and then every time I draw a new bootstrap sample, I construct a new one. So in one instance, out of the 2000 repetitions I do, might be this green one here. Okay, so let the efficiency of firm D relative to the black one here be 0.7. Okay, so that's the original efficiency score you get when you go out and do a DEA model. Now do this bootstrap procedure of picking inefficiencies, creating a new technology. So now I get the green technology, and I assume that compared to that green technology, my efficiency is 0.8. That means that I have estimated in this particular instance with this specific bootstrap sample, I have estimated a bias of 0.8 minus 0.7. So the bias is really 0.1. Okay. So that's what I write here. Now I can do that 2000 times. And that has two implications. It means that I get 2000 observations of the bias in this, the bias that this D firm is facing. And I can take the mean of that, of course, and let's assume that that will also be like, in this case here, 0.1. Then you can just take the, you can do, you can now use that because of the similarity, because we assume now that this distance here is approximately the same as this yellow distance here, which was the distance between the underlying true technology and the DEA estimated technology. So since we can calculate this difference here, and we say that these two are approximately the same, then we can find this an approximation for this orange one here, and that we can subtract from the original efficiency score. So if the original efficiency score was 0.7, I can subtract this orange bit from the efficiency score, and then I get down to 0.6. And I can do even better than that, because that was just the outcome of doing one repetition. Now I can do another repetition, and I can do another one, and in each case I get a slightly different bias. So I basically get I can create like the distribution of the biases, and that also means I can take the confidence interval, 95% confidence interval for these biases, and I can if I subtract that interval, I take the lower part and the upper part from the original efficiency, I basically get not only a bias-corrected efficiency, but I get a confidence interval for the bias-corrected efficiencies. Okay, so that's basically the trick of it. I know it might be slightly complicated, and we can discuss it when we get to questions, but that's the general idea of this bootstrapping based way of correcting for biases and getting confidence intervals. And here's a longer description of exactly how you do it. I might want to just add, let's just stick with that. So you can read that in details. It shows here how you, first of all, how you do the smoothing. It's described in details here, where you have the original efficiencies, and then you add this noise term. And if it becomes above 1, you do the reflection, so you move it back to the left-hand side of the of 1, and then you adjust the variance of this distribution, and then you do this you take the observations which are first projected on the frontier, and now you push them to the right. This is done in step number 3 here. And now, compared to that technology, you estimate the efficiency of the original score. And by getting a difference between what you estimated originally for firm number K and what you estimate now, you get an idea of this bias. And that bias you can then subtract from the original score to get a bias against the true underlying technology. So these are basically some of the steps that are described, and these are the steps that we have implemented in the Bootstrap procedure in the R package. Let me give you a couple of examples of what that might look like. So assume that I have a very simple case with 5 observations. If I correct for the bias, I can estimate a bias for this guy, I can estimate a bias for this guy, and that for this guy, and so on. So if I do that, then I get to this one here. Okay. If I now also realize that I have actually a confidence interval for these biases, I can then take the endpoint on that confidence interval, and that means that I can get like a confidence interval around this biased corrected technology here. It can be like here, or there will also be another one on the inside here. But for my purpose, it is in the best possible case. I'm asking, in the best possible case, with 5, the best possible case, how much could I have saved? I could have saved down here. You will also have which will actually be the lower part of the confidence interval for the bias. You will also get that. So you should actually have like a confidence band around this one here. So you can also say that even if I want to be cautious in my bias corrections, how much have I then shifted the frontier? Okay. Here I have illustrated these same data using this picture, where I actually show the actual observations, which is the round one here. And then I have the bias corrected efficiency scores, which is this, and the confidence interval for that. That's this line down here. And the bias corrected efficiency score, if I just use the mean of the biases, is this one here. This spade or whatever that's called. So you see here that for the first observation, which if you go back, the first observation is considered to be fully efficient. But if you bias correct, it is going to be only 87% efficient. And if you want to give a confidence estimate of the true underlying technology, it's somewhere between, let's say, 0.75 and up to 1. Okay. If you take firm number 2, you can create in the same way a confidence interval for the bias corrected ones. But what you see here is that firm number 2 it comes out with much less uncertainty, and that has to do with the fact that it is located. It has several comparators. It can be compared to both number 3 and number 1, and it means that number 1 is sort of sitting in a corner here. And there's very few that it can be compared to. The same goes for 5. So we would expect a lot of uncertainty about 1, a lot of bias, but also uncertainty about the evaluation of the bias corrected efficiency of 1, and the same for 5. But 2 is closer to some other ones. The same goes for number 4. So let's see if that holds. 2 and 4 has a relatively lower uncertainty about the bias. So you have a lower span here. The confidence intervals are more narrow, while 1 and 5 are for sure those, and they were the one from the corner points. They're the one that has the largest uncertainty. So that's also what I note here, quite uncertain about endpoints. Okay. Here's an example with two inputs. You again have the observations. You create the original DEA one here. And so evaluated to that, you get the original efficiency score. If you bias correct, you get a smaller efficiency score because you can go down there. And if you want to use the upper, or whatever you want to call it, the upper, the lower confidence interval, I mean, it is actually the upper confidence 95, upper part of the confidence interval for the bias. Because when you subtract that, that gives like the best case scenario. Okay, you can say, then you can get down to this line here with substantially more efficiency improvement potentials. Okay, and here again you have this picture here. So here you see that 2 and 5 has relatively high uncertainty about what the bias corrected efficiencies are. That's 2 and 5. That's 2, because it's sitting here, it has no one to directly be compared to, because this one is so far out anyway. It actually has 1 because it gets projected there, but 4, and you have also 5, which is also sort of sitting on the corner. So that's kind of the intuition also, that if you are very special, you can be compared to relatively few, then you're most likely going to have more uncertainty about the duration of your performance. And here I have an exercise where you can actually try to do it. I have observations here, the input vector, the output vector. I calculate the DEA efficiency model with country return to scale. I take out the efficiency scores. Then I do the bootstrap with 2,000 reputations. And that you can easily do that because it's such a small data set. And then I calculate the efficiencies in this bootstrap. No, first actually I have the efficiency scores. Then I have the biases. Let me see. No, these are the bias corrected. The bias corrected efficiency scores, and then you have the confidence interval. Yeah. First you have the efficiency scores without anything. Then you have the bias levels. Then you have the bias corrected efficiency scores. And then you have the confidence intervals for the bias corrected efficiency scores. Actually, I could just have looked over here because it explains it here. The first I get is the efficiency scores. The next I put some nice headings here. So it's bias, the second one, and then it's the bias corrected efficiencies and so on. So take a look at this, and you see that you always look worse when you do the bias correction. It's always lower than the efficiencies here. And you can see also that sometimes you have a wider confidence. Sometimes different firms have different bias levels, basically, because it depends on how certain you are in this area that this firm is located. So think about if firms would like bias corrected efficiency scores, if it's a good idea to do bias corrected. I mean, it's a big discussion among regulators, for example. We try to advocate, why don't you do bias corrections? And then they say, yeah, but that's hard to do and explain. And we now start to speculate something about, we don't just rely on actual data, we speculate about how these actual data are biased against some underlying unknown technology. So no one has really picked it up. You can also imagine that the firms might not want to have bias corrections because bias correction always makes them look worse, because we compare to a tougher technology. One can, however, ask if it is not unfair not to correct for the biases, because just the fact that you have very few comparators, it will give you an easier life, as we also talked about in the subsampling approach. So maybe it is a more fair comparison to do that. Think about that. And if one thinks this way, I mean, they might all lose, but some might lose more than others, and that means that some might actually implicitly, relative to the others, they might benefit. So that's worthwhile to think about. The next thing I'm going to do is to discuss how you can use this whole technique to do some testing. And I'll just try to illustrate if you want to run a test for returns to scale. The hypothesis is that we have a constant return to scale. The alternative is that we have a variable return to scale technology. One of the ways you could do that is to use the test statistics, which is just you look at the efficiency scores for all the firms under a constant return to scale, and you divide by the sum of the efficiency scores when you have variable return to scale. We know that you always look worth in a constant return to scale than a variable return to scale because the CIS is a bigger technology. So that means that if this one here is a very low number, it kind of indicates that it's probably not a CIS technology. If there's too much of a difference between the two technologies, then it's probably not because the data doesn't really support the idea of having a very big disadvantage of being small and disadvantages of being large. So you have to look at this, and then if it is very low, you'll have to reject your H0 hypothesis. And the idea we'll use is just to, but the problem is we don't know how the distribution of this one is. So we should really try to, and therefore we don't really know what is the small number of this. Is it like half, or is it like 0.25, or what is a small number? Okay, so what we do is that we bootstrap the distribution of this under the H0 hypothesis, and then we can see if we have an extreme observation. So if we assume that data has been generated by the null hypothesis, would it then be likely that we get this the value we have for the S variable, or do we get such a small number that it is not likely? So here we have the data. I feed in the data. I do the DEA constant return to scale and variable return to scale and figure out the efficiencies, and then I can sum this test statistics for the scale efficiency. It's not, just to remind you, scale efficiency for an individual firm is the efficiency in the CIS divided by the VS model. So I could have used another one where I basically calculated for each firm, I calculate its scale efficiency, and then I took like the average of this. This is not exactly what we do. We just use another statistic here. We don't do them divisions pairwise. We just sum all the CIS efficiencies, and we sum all the VS efficiencies, and then we do the division. But these are just different testers one could use. Okay, so here I calculate the tester, and I can see what the tester is. And now I want to start the bootstrapping. So what I do is that first I have to, bootstrapping is a random procedure. So any random procedure, when you have to pick out numbers, can be hard to replicate. But because the computer is not entirely random, you can actually replicate the choices that the computer are making, even though it is imitating a random choice. But to do that, you need to know the seed by which you start this random number generator. And so that's what I do here. I pick some random number to start with, which I call the seed. I saved it as a save seed, and that save seed is now this magic number that is being used I will use in subsequent runs so that I can replicate things, although it is imitating randomness. So now I go and bootstrap the CIS, then I set the speed, I set seed, like the one I saved up here. And now I do 2,000 repetitions of this DEA bootstrap. You can take a look at what you have. So these will give you 3 examples of the bootstrap sub samples that you get out. And now I can do exactly the same under VIS, where I generate the same numbers or the same technologies, but I calculate using VIS technology or VIS assumption. I calculate the same random draws. That's what I want to say. But I calculate with under VIS, and then I can calculate the scale efficiency as basically the sums of the values I get in the BIS and the VIS numbers. This is just this before, I think we call it the S variable, and then or the S variable was the specific value of that statistic for the data I have on hand. Okay. So basically, this one here will give us like 2,000 observations from the distribution of S. And then I make a picture of it. And then you can say that, okay, what is the small number in this framework? If you want to test that with a test probability of 10% or 10% confidence interval, you can just find the crit value, that is like the critical value, and that's like a R function where you basically just give it the data, and then it'll make like the distribution of those data, and then it'll find the 10% lower cutoff rate. And you can also so that will, then you know that if you fall below that level, then you have to reject the hypothesis of contra-return to scale. You could also see what is the test probability for my specific sample, and to do that you use this R function called type 1 error, which is just you give the actual observation you have, and then you give the scale efficiency, which was those 2,000 numbers from which it can construct the distribution. This you can do. Actually, if you're interested, you can, when you try to do it, you can also use this function, which is called compile reports. There's been some very nice ways that you can integrate LaTeX and R, and actually RStudio has some of that. So there's a button at the top bar which says something like compile report. And if I do that, then you will see not only the calls that we are making, this is basically running the scripts, but you will also see the plots that this function here generated the plot. It was in the script, but you put those results inside this small report, and then you can do a similar one here. So here you see the bootstraps. The first 3 bootstraps out of the 2,000. Here you see the histogram of this tester that I estimate, and my tester was 0.7. So you can see that it's located somewhere up here. So it's actually not an extremely low observation I have. So most likely CS is perfectly fine distribution. You can actually see that the cutoff rate, if you use 10%, is around 0.6. And 10% is even a high one. And then you can also calculate the p-value, namely the probability of getting a value of your statistics, which is lower than my actual one, which was 0.7. So what's the chance of being to the left of this? Well, that's actually calculated down here. It's 52%, more or less 53%. Okay. I just want to say, because I referred to this alternative package called FEAR that you can acquire from Paul Wilson. Here we have an example, another example. I think that's another example, right? Yeah, it's another example using FEAR, but you can see the R code if you install the package FEAR, what the R code would look like, and then you get it, in this case, a score of 0.8, and you could the p-value is about 30%. In this case here, what he does, he just shows the fractals. So what you get is 0.80, and you can see that where do we have this 30? So 0.8. So that's somewhere up here. So it's approximately. So that's because the heading for these numbers are those two down here. So it's somewhere around 30% probability to get a number like that or something smaller. So we accept 80. Okay. I'll show you in a later slide a little bit more of what you can get out of the Paul Wilson procedure, but it's basically the same as you can get out of ours. The big difference is that it's running much faster if you have really big samples. So one of our first applications in a regulatory context where we tried to use some of this was actually in a Norwegian context, where you can see that we had a model with some efficiency scores. And the efficiency scores were those, the dark blue here. And then we did a bootstrapping procedure and then figured out what the biases was. The biases was these here. So you can see for some of the firms, actually some of the large firms, these are total cost I illustrate down here. And these are the efficiencies. For some of the large firms, you can see that the biases is relatively large, which makes sense because they have fewer they can be compared to. The biases are much smaller for the small companies. So you can, it makes sense because there's more that they can be compared to. And then combining the two, you can create these purple dots here, which are the bias corrected efficiency scores. We did it also here where we corrected and uncorrected VIS scores. So you can see the difference between, these are the original efficiency scores and these are the bias corrected ones, and it might be mostly interesting to see that in terms of the bias corrected efficiency scores, only one is fully efficient, but in terms of the original efficiency score, there was a whole bunch on the frontier. So there's because we believe that in most cases there is a bias, and therefore these guys are actually moved a little bit to the left when we do the bias correction. Here we also tried to do this, but where we added confidence intervals. I should say though, so basically we look at here, the black one are the standard error of the biases. And so what we tried to do at that point was just to take these standard errors, and then we multiplied them with 2, and we subtracted or added that to the original efficiency scores, and that gave us like a confidence interval for the bias corrected efficiency scores that look like this. Okay, so that's not necessarily okay. First of all, of course, this is really interesting because people would like to know what's my efficiency score, but also what could it have been in a best case scenario and what might it have been in a worst case scenario, or what sort of the variation of my confidence interval for my efficiency scores. So in this case, we estimate the confidence interval for a given firm, like the difference between this one and this one. I just wanted to add that this way of constructing the confidence intervals by just adding 2 standard deviations of the biases up or down, that's not actually a good way to do it. It works fine as long as these biases are normally distributed, but if they're not, it's not the proper way to do it. And there's really no reason to do it because we do have 2,000 observations of those biases. So we can use the actual empirical distribution based on those 2,000 observations. And that's actually what our code does. So our code is not naive like this. It is actually using the underlying empirical observations because it might not be symmetric, that distribution. But anyway, this is another example of how we correct it. So in this case, we even, what does it? We have efficiency, we have corrected efficiencies. Oh yeah, so in this, we also tried to make like a prediction. So we added some further uncertainty to the model. One thing is that we have an idea where they might be located, but then there might also be uncertainty once you observe it. So we subtracted an extra 2 standard deviation here. Not quite sure whether it's perfectly correct to do. It's probably not. Here I try to compare what are the original scores in the Norwegian model, what is the bias corrected scores, and what is the SFA scores. So what you see is that the blue one here, so down here I have the bias corrected efficiency scores, okay, and so the blue one here are showing what kind of bias corrected efficiency scores do you have. You get a higher efficiency score if you just use the normal efficiency scores. But in this case here, on this data set, we actually got higher scores again if we use the stochastic frontier model. This, I don't remember the details of exactly this one here. There was, as I mentioned in the presentation on regulatory benchmarking, from 2004 to 7, there was a lot of projects about how to develop a new regulation in Norway, and we did a lot of work on that, and this was part of it. There was a lot of other consultants doing work on it also. Okay, so as I said, in FEAR you can do this bootstrapping also, and this was the slide I showed you before. Here we give a little bit more details of all the information you can get out. Like in our case, you can get out the bootstrap samples, you can get out the biases, you can get out the confidence intervals of the biases, and you can get the bias corrected efficiency scores and so on. You have to be a little bit careful when you move to other packages. I think actually, or I do know that FEAR is actually using shepherd distance instead. So be a little bit, think about that when you compare our results to their results. You normally have to be inverted. Good. So I know this was tough. It was long. It was theoretical. It's not that theoretical, but it might be more difficult to understand. So let's take some questions.